doing trace methods for combinatorial cut and paste K-theory. This is kind of the first major result coming out of that grant. So this is actually, I've been joined with a bunch of people. Anna-Marie Bowman, Tina Gerhardt, Mona Merling, and Ina Zakharevich. But then I kind of have been running with this, so I'll tell you some stuff at the end as well that comes out of this. Okay, so maybe I should remind you what the Farrell-Jones conjecture is, right? Although, it came up in Arthur's talk earlier. Right, so suppose R is a ring, and G is any group. Then there's this assembly map. I'm just going to do the torsion-free case. So there's this assembly map from Pg plus smash k of r. That's the same thing as the homotopy orbits of the k of r spectrum, homotopy G orbits, to the K-theory of the group ring Rg. So it's kind of the most natural map you can think of that goes from here to here, identifying, if you like, the simplest piece of this K-theory. Right, so if I were to, let me write something about what it is because I want to contrast it with the assembly map that's coming later. So if I say, have a bunch of modules and maps, F1 through Fn, and then I also have a bunch of elements in my group G, corresponding to a simplex in that bar construction, then I send that to, well, I tensor all the modules with the group ring Rg. Let's say everything's a right module, so I tensor over R with Rg. And that allows me to take not just the map, but also I can have, if G is acting on the right on this, I can also have an extra G action on the left. So I'm basically taking the group elements and putting them into the maps. I do this for all the other ones. Okay, so, there's this famous conjecture, right? So there's the Farrell-Jones conjecture, which you've maybe heard of before if you're around here. That this assembly map is an equivalence. I mean, if, say, R is regular and G is torsion-free. If G is not torsion-free, then there's this fancier form of the conjecture. So what I'd like to talk about today is a similar assembly map. So there's a similar alpha. But this alpha is defined in a different form of K-theory. It's defined on scissors congruence K-theory. So if you like, it's identifying the simplest piece of that K-theory, the way this is identifying the simplest piece of the K-theory of a group ring. But then the surprise here is that it's always an equivalence. So in particular, there is no dependence on the group G. The way there is for Farrell-Jones conjecture for group rings. And another point of comparison between these two. So one way of attacking this is by trace methods, right?
Sorry, I don't understand what you mean by no dependence.
What does it mean?
Well, I haven't said, so in this case, so this assembly map's not an equivalence in a lot of cases where G is not torsion-free. And when you prove it, you often prove it for a certain class of groups, right? Instead of giving a general proof. So the surprise here is when you write down this assembly map for scissors congruence, you get a general proof.
You just like homology.
Yeah.
Instead of no dependence.
Oh yeah. Proof for homology. That's better.
Homology.
True because. Because the proof works for all of you. Good? Alright. Okay. So let me put up a definition of scissors congruence K-theory. Okay, so let's fix a geometry. I always do this. I always draw a bar and then I have to write over it. Every time. So fix a geometry xn. Sorry, Felix was complaining to me at lunch about this notation. So n means the dimension, sorry. I'm going to do that. And by a geometry, I mean either Euclidean geometry, hyperbolic, or spherical geometry. So one of these three standard cases. And then I'll consider subsets of Xn. I'll say that P is a polytope if it's a finite union of n-dimensional simplices in the geometry, right? So simplices taken, they have to be top dimension, and it's taken in the geometry, right? So all the edges, faces, and whatnot are geodesic.
So by simplices you mean convex?
Yeah, convex hull in the geometry of finitely many points, and in n simplex, so in general position. Yeah. All right, so I'm going to define this category. So let P, X, and G be the category whose objects are these polytopes in Xn, and whose morphisms, so a morphism from P to Q is just an element of the group G followed by an inclusion. So you think of this as I can go from one polytope to another by applying, oh, I didn't tell you what G was. Yeah, let G be any subgroup of the isometry group of that geometry.
But that's not all G, right? So, I mean, what is that?
Okay, sure, you can map to the isometry group. Now it's all G. So yeah, the point is the proof doesn't depend on which properties of the G that I pick. Yeah. Okay, and maybe I'm overselling that point. Okay, so I pick this geometry, I pick any subgroup of the isometry group, for instance, all of them, or in the Euclidean case, maybe just translations, and I make this category where the objects are polytopes, and I map from one to the other by applying an element of G, and then including inside some larger one. Okay, so suppose I have a collection of maps. So I have a collection of PIs, and then they map by GIs to GI PI, and each of these are inside P. I say that this is a subdivision.
So, sorry, when you say inside, you just mean set theoretically inside?
Yes, set theoretically inside.
Without any transversality or whatever, touching the boundary properly.
Oh, they can totally touch the boundary. I want them to do, because I want to form subdivisions, right? So I want to be able to have.
Sure, but subdivisions you want them to touch the boundary nicely, not like. Not
Yeah, right. So I want to consider, the inclusion of any one of those pieces inside. Yep. So I'll say the set of such maps is a subdivision or almost disjoint cover. It's if they cover, so P is the union. Oh, there should be finitely many of these, by the way. Finitely many. I'm only going to consider finite subdivisions. So P is the union of those images, and the interiors are disjoint. Or, they overlap and measure zero sets. Any two of these, the intersection between them is a finite union of lower dimensional simplices. And so it lines up with what you would think of as a subdivision. I can move the polytopes over, and then after I've arranged them, I have a subdivision of the target. Okay, so this is an example of what Ina calls an assembler. I won't write out the definition, but it's basically a category with some notion of finite, almost disjoint cover, like this. I mean, it's more than a growth in deep topology. You also need that if you have two of these subdivisions, there's a common refinement. So there's a few more axioms. Okay. I'm going to go through this really fast tonight. I'm going to do a really early board wash. So with this data, you can then define a category, which is basically a category of covers. So the objects are going to be disjoint unions of these polytopes, and the maps between them are going to be maps of disjoint unions that form a bunch of subdivisions. So the target is going to be subdivided by all the polytopes in the source. Oh man. I haven't cleared a board like this in a while. This is really satisfying. You should try it. All right, great. So let's define a category of covers. You can do this for any one of these assemblers. W of P X M G. So the objects are formal finite disjoint unions of polytopes. So an object is some finite set I, and then some collection. I'm going to write it as a disjoint union, but it's just formal. A disjoint union over I and I of some polytopes. They don't actually have to be disjoint in the geometry. They can overlap. And then a morphism. So if I have a map from this formal disjoint union to this formal disjoint union, well, first I want to map the sets I to J. So each of these is mapping to one of those. And then I want to map Pi to Qj. So the map is going to be in this category. So it's really going by apply an element to the group, and then include that in Qj, Q f of I. And then I want that for every one of these Qj's, if I take all of the Pi's and go to J, then this is a subdivision, or an almost disjoint cover.
The F can be anything, not injected also. The F from I to J.
This,
Yeah, can be anything.
it has to be surjective. There's assumptions that the polytopes are non-empty, and this is a non-empty set. But it definitely doesn't have to be injected. So each Qj is going to be covered by multiple
But
Pi's.
surjective, that is it.
Yeah. Doesn't have to be surjective. Okay, so if I take the classifying space of this category, I'm trying out this notation. Let me know what you think. So this forms a monoid under disjoint union. Usual caveats, E infinity monoid, homotopy coherent monoid. But you can take formal disjoint unions of this. That gives something like a commutative up to homotopy monoid structure on that. And so you can get a spectrum by group completing it. So this is Zakharevich's definition of scissors congruence K theory. So the K theory spectrum of this category is the group completion of this classifying space. So that gives you a spectrum. For instance, you can make a Siegel space out of this, and that gives you a spectrum. Okay, so this is constructed so that if I look at pi naught, k naught, what am I getting? I'm getting the group completion of pi naught of this category of covers, right? So I'm going to get a free abelian group on all the polytopes P in my geometry. And then what are the one cells in this category going to do? They're going to mod out by, so the class of every polytope is equal to the class of, I can sum over the PIs for all subdivisions. Pi is going to P. The fact that I have the group elements as well also gives me a relation that the class of P is equal to the class of GP. So altogether, this gives a spectrum whose K naught is the classical scissors congruence group. So this is what Julio is calling a SCN for when Xn is Euclidean geometry and G is all of the isometries. All right. So now I'm supposed to talk a little bit about Hilbert's third problem. Oh, yeah, all right. Well, yeah, Julio, help me out for that.
One question, if I
Yes.
so I think I lost track a bit of how much this definition depends on G as opposed to the image of G in the isometry group.
So if that's not injective, then when you have a morphism, part of the data is that choice of element G, right? So different G's with the same image are still getting treated differently.
Like,
Yeah.
okay, not you want to see the difference, right?
Exactly. It'll show, it might possibly show up higher than that. Yeah. Right, so recall that two polytopes P and Q are G scissors congruent if I can write P as a union of PIs, so I can write a subdivision of P, almost disjoint cover, then I can change PI to each PI to a QI by applying one of the elements in my group G. And then these QIs form a cover of Q. So in other words, I take my polytope, I cut it into pieces, I apply an isometry to each piece, which is in the subgroup G, and then those rearrange to the target polytope. All right, so that's scissors congruence. Cut into pieces, rearrange, and glue. So this group is important because it's a group and it's capturing scissors congruence. So more precisely, if you look at that definition, it's pretty easy to see that if P and Q are G scissors congruent, then their classes are equal in this group. The converse is also true. If the group, this is a theorem of Xylev, the converse is also true if, as long as G is big enough that it's acting transitively on the geometry Xn. So for all the examples that we're actually interested in, like all the isometries, or the orientation preserving ones, or in the Euclidean case, the translations, in all those cases, the set of scissors congruence classes is sitting inside this group. Okay, so P and Q are scissors congruent, G scissors congruent. That implies that their classes are equal. And the converse is also true if G acts transitively on Xn. So solving the scissors congruence problem, describing when two polytopes are scissors congruent, really amounts to computing this group. Right, so let's just look at a couple of simple examples. So in Euclidean space, so for all these, I'm just going to take the whole isometry group as G. In Euclidean space, P and Q are scissors congruent. So Yulia mentioned this already. They're scissors congruent if and only if they have the same area. And that corresponds to the fact that this scissors congruence group, so polytopes in E2 with all isometries, is the reals. You compute this group, you just get the reals, so area is your only scissors congruence invariant. In E3, three-dimensional Euclidean space, two polytopes are scissors congruent, if and only if they have the same. So this is really what Hilbert's third problem is about, right? If and only if they have the same volume and the same Dane invariant. So you can think of this as saying there's a homomorphism from this scissors congruence group a homomorphism to R for the volume, and then R tensor, I like to write it as R mod pi z. For the Dane invariant, it's important to emphasize this tensor product is over Z, or equivalently it's over Q, but it's not over R. So this one is the volume, this one is the Dane invariant. May as well write it out. It's the sum over edges of the length of that edge tensored with the dihedral angle. So the injectivity, so the statement that this is equivalent is the injectivity of that homomorphism. In fact, Jessen gave a not very long exact sequence that computes this group.
Actually, what's in the dihedral angle? The dihedral angle, that's an idea. What's the unequal angle?
Oh, what's the, yeah, so at every one of these edges, you have two faces that are meeting at that edge. So you're measuring, take a plane perpendicular to the edge, you're measuring the angle between those faces. Yep. So you can convince yourself that this is an invariant, right? If I cut into more pieces, the extra terms I get are going to cancel each other out. So it's clearly an invariant, but actually more than that, if you have the same volume as the invariant, your scissors congruent. So this group embeds into this group, and there are more generators. All right. Okay, so computing. So what's the message we're supposed to get from this? Computing K naught amounts to solving the scissors congruence problem, or the generalization of Hilbert's third problem in the geometry Xn up to the chosen group G. So computing these groups is a very worthy problem, and a very difficult one too, right? We don't know K naught of polytopes in Pn, the whole isometry group, is not known for n at least 5. So it's an important but very difficult problem.
In particular, you say for 3 it is known?
For 3 it is known.
What is it?
It's a subgroup of this.
Yes.
There's a long exact sequence. So R goes into the K naught group. That goes to R tensor R mod pi z. And then there's a map to Taylor differentials of R over Z. And then that's surjective. So it's R plus the kernel of this map, which sends X tensor C to X, I think I'm going to get this right, D sine C over cosine C. So like the group was completely computed. So this is by a paper of Jessen in 1968. Yeah, so right, that's the solution to Hilbert's third problem, right? It's a complete computation of the whole group. So it would be nice to compute these some more examples, or to be able to compute the higher K groups in more cases. So for instance, K1 has to do with scissors automorphisms, as you might expect. So these are maps from a polytope to itself that cut the polytope into pieces, rearrange the pieces, and get the same polytope back. So let me just give one example. This is actually more or less the only example we knew before this project of a higher K group. So if I take polytopes in the line and I mod out by translations, it turns out I get the exterior product of the reals with itself over the integers, or equivalently over Q. And the element x wedge y corresponds to the scissors automorphism of an interval that takes an interval of length x and an interval of length y and interchanges them. Yep. I'm actually about to put up the layout.
Sorry, if x and y are different, how do you exchange them via?
It's a scissors automorphism of the interval of length x plus y, right? The pieces can go anywhere in the interval. Yeah. Let us point out, no higher K groups were known. And those are other examples. So it's kind of a big question mark what all these higher K groups are. I really miss cleaning boards, can you tell? Go crazy for it.
Like, sorry, Cary, but maybe
Yep.
were they even defined? Like,
The higher K groups?
yeah. Like when you say no hierarchy groups were
Oh, yeah, well, so I said the group completion gives a spectrum, right? So they're the higher homotopy groups of that spectrum.
right. I mean that spectrum was only considered by Inner.
It's the, yeah, K-theory of an assembler has also showed up in studying the growth and decaying of varieties.
So, but like, I mean, I'm wondering, like, if K1 didn't come up somewhere, like, in some different flavor historically, did it?
No, not as far as I know.
Or whatever.
Yeah. So that's kind of one of the motivations for this is, yeah, to take this and say, okay, you know, can we compute these higher K groups? Can we take any of the tools that we have available to us and adapt them to this setting? And it turns out we can. Yay. Okay, so we need some tools. So one of the tools we're going to use is a trace map. So this is a map that's going to go from K theory of polytopes in Xn up to the isometry group G to Eilenberg-MacLean spectrum of the reals, homotopy orbits under the trivial G action. Or to put that another way, the ith K group in this geometry is going to go to the ith homology group of the group G with real coefficients. Okay, so how do you define this trace map? It's not too bad. Well, okay, it gets really bad with notation. So if you're kind of, so let me take an n-tuple of maps in the classifying space. Here we go. Okay, and I'll write out what the last one is. So disjoint union over I and I of some polytopes pi. So suppose I have an n-tuple of maps like that. I'm going to send it to something in the chains here. So I'm going to send it to a sum over the finest subdivision of, so for each polytope here, there are going to be a sequence of group elements applied to that. I'm going to take those group elements, tensor them together. I shouldn't use n here, n is the geometry. And then I'm going to take that times the volume of pi. So here, if I take just this ith piece, when I have these maps act on it, each map is going to act by a certain group element. And those are the group elements I'm going to feed it. So this gives me something in the pth chains of this group with R coefficients. And then you can pass from that to homology. Okay, so this is a really computable thing. Like, you could, right now, instead of listening to me, look at...
Cary, what description of AI is used for that?
Oh, so this is a map. So what is this actually defining? It's defining a map from the classifying space of the category of covers to this as a simplicial abelian group. And then, since it lands in a simplicial abelian group, it factors through the group completion. So therefore, it defines a map out of K theory. Yeah, so it actually, the way I'm defining it, is a map from the nerve of the category of covers to the, yeah, how do I want to say this? Bar construction with respect to tensor products of Z, ZG, R. So map of simplicial sets like that. And then, you know, wave your hands a little bit and it gives you this. All right, so I invite you to try this out and write down what this trace map does from polytopes on the line to the first homology of the reals with R coefficients. So I just told you this is R wedge R, told you what the generator is. This group is going to be R tensor R. So you can write down what that map is. These are both happening over the rationals. So it's a very computable thing. But when are we going to again?
We started at 10 minutes, so we're under 4, a little bit after 4.
Okay, oh, I'm great then. Great. Okay, so the first tool is this trace map. It's pretty simple, it's very straightforward to calculate this. And then the next tool is an assembly map. This is what I alluded to at the beginning of the talk. So the assembly map is going to be a map from K of polytopes, but I'm not going to apply any isometries at all. So everything is to stay fixed. If I do that,
Sorry, good question. That trace map for I equals 0, is just the it's just the volume.
Just the volume, that's right. So it's mapping K0 to R by taking the volume.
So it's a higher version of the volume, so to say.
That's right. Oh yeah, that's true. That should be the first exercise. And then the second one is compute this for K1. Okay, so in this category, if I don't, if there are no G actions in the morphisms, then as a result, I can have G act on the whole thing. So then this spectrum gets an action by my group G. And therefore, I can take its homotopy orbit spectrum. So the assembly map is a map from that to polytopes up to the group G. So I wrote out that definition earlier because I just want to show, by way of comparison, the similarity here. So you, again, have a tuple of maps. Disjoint union, I gotta label these a little more. P minus 2, I. Oh, it's maps are going to the left. P minus 1, I. PI. But all these maps, there are no G's, so these are all inclusions. I'm not applying any group elements when I'm mapping each one to the next. So you just think of this as a polytope and just a bunch of successive subdivisions without any movement. And then I also have a tuple of elements of G. So I just send this to the same flag, but I just work these elements of G in. So all the way over at the ends, I have a disjoint union of PPIs. But now over here, I'm going to have a disjoint union of GP applied to P minus 1I. And now in this map here, every polytope is going to have GP applied to it on every piece. And then the next map, I'm going to have both GP minus 1 and GP. I'm always making my arrows too long. Applied to the next one. And so that one's going to have GP minus 1 applied to every piece. And so on. You might get a little worried about this commuting with the last face map. But for that, in this bar construction, the last face map is having G act on the category. So if I delete that last element of G, I have to have it act on all the remaining polytopes. So that actually does make this simplicial.
Sorry. Here, G is seen as a discrete group, right?
Yes, G is discrete. In scissors congruence, your groups always have an obvious topology and you always ignore it. You treat them all as discrete groups. That's what makes this so hard. That the groups are awful. All right.
Why do they have the topology? I mean, they map to a group that has the topology.
Usually we take G to be a subgroup of the isometry group, and the isometry group for all those cases kind of has an obvious topology, but we ignore it. Yeah.
Can you not ignore it and just not get a different answer?
You tend to get pretty trivial answers if you have it there. Yeah. Yeah, it tends to not be very interesting or reduced to something classical that we already know. I think, I don't remember off the top of my head, but I think in a lot of cases you just end up getting something contractible. But I have to go back and remember that. Okay. Oh, yeah.
From this point of view, so you would think that you would, instead of mapping the discrete, I mean, they continue the discrete.
Oh, you mean?
Homology is map to, I mean, you can map.
Oh, for this, yeah, there's no problem. Like, you could, yeah, then take G to have a topology. Yeah.
Some information, or on the other hand,
You-
depending on your point of view, get rid of these weird tensors over Q over R.
Yeah, you lose a lot. Well, so for instance, so all the higher homotopy groups of this are non-trivial. But if I go forward and then I start to think of R as a topological group, then there will be no homology here. Whereas it turns out if I keep it discrete, this map will be injective on the higher homotopy groups. Okay. I can state the main theorem now. Okay, so this assembly map is an equivalence. There we go, stated the main theorem. I suppose more generally, there's something a little bit more general going on here, where this category I can think of it as a homotopy orbit category. It's the homotopy orbit assembler of P xn1. So I really have an assembly map. If I have any assembler C with G action, then I have a commutation map from K of C homotopy orbits to K of the homotopy orbit assembler. And that is an equivalence for all groups G and all assemblers with G action C. Okay, so this is the sense in which the proof doesn't depend on the group at all. It's this feature of assembler K-theory that taking homotopy orbits commutes with K-theory. And also that the category that we're interested in this case, like the category classical interest that comes to us, is already a homotopy orbit category. So we can pull those homotopy orbits out.
But isn't like assembler K-theory essentially some sort of a left edge on it? So doesn't it commute with all colimits somehow?
Oh, I don't know, that's a good question.
Right, I mean, this of course depends on precisely what exactly all these words mean, but somehow it seems to me like assembler K-theory is just some sort of way of group completing and making an operate like symmetric noise, and then it would commute with all.
Yeah, so if you show that's true for all colimits, then you get that as a special case.
Yeah.
That's a good idea. Yeah, this is a special case of pulling a colimit out, isn't it? All right. So let's prove this. So the idea, so I'll just write it using C because that's fewer symbols. And this is supposed to work in general, right? So I have this assembly map, and then I also have this trace that goes back to Eilenberg plane of the reals, homotopy orbits. So the idea is, well, this should be an inverse to that.
Sorry, what is this trace map in general?
Oh, in general, yeah, so for any homotopy orbit assembler, homotopy orbits means growth and deconstruction.
Yeah,
So every time you have a morphism, you take the associated elements of the group.
no, sure. The question is how you send it to R.
What's the volume?
Yes. So in general, the volume, I guess I'm about to say that because the idea of the proof is to just be careful, like think about what you should mean by volume. Right? So what made this work, right, the volume didn't have to be a real number. It just had to be an element in some abelian group. And in order for this to be simplicial, it had to have the property that the volume of one polytope, if I subdivide it, was the sum of the volumes of the pieces. So that shows up when you do the last base map. So you recognize, oh, well, you know, the volume doesn't have to be in R, right? It can be in anything that has this additivity relation. So the idea is instead of taking the volume to be an element of the reals, take what is the universal volume, right? What is the universal thing that has additivity? K-theory, right? So take the universal volume. In other words, the universal additive invariant to P. So you take P as a point in the K-theory spectrum. That's even more refined than thinking about its class in K-naught. So if you can do that, then you get a lift of the trace that lands in the homotopy orbit spectrum. And then it becomes straightforward. You just check that these are inverses of each other. So that's the idea. If you take this trace construction and you just replace the volume as a real number with the volume as a point in the spectrum. So the main difficulty is that, well, you know, if it's a point in this K-theory spectrum, then this equation isn't true strictly, right? If I sum the PIs as a point in the K-theory spectrum and compare it to P, it's not literally equal, it's just homotopic. Okay, so the main difficulty here is a homotopy coherence problem. If you just write down this formula directly and use this reinterpretation, it's not simplicial, it's only simplicial up to homotopy. But of course that's not good enough, it has to be simplicial up to coherent homotopy. So it turns out you can solve this pretty simply actually. You can solve this by just taking a subdivision. Turns out that's good enough. Subdividing the source. So then every one of your, for instance, every one of your one simplices becomes a composite of two of them. So you can use the first one to go between P and the sum of the PIs. And you can use the second one to apply your group elements. There's also a problem with, there are no more problems. Those are all the problems I have time to talk about. No more problems, everything is great. Okay, so, scissors congruence K-theory.
So you can only at least explain why the other composite that's supposed to be an identity in this equivalence is also true and not the one that's sort of true.
Oh, why if I go to here and back, that's true?
There I can't use something that goes without thing, I guess.
Yeah, oh, I wasn't using universal laws really for any of this.
Yeah.
You write it down directly and you see there's a homotopy. Yeah, so what's the idea? So I have a tuple of, So I have a tuple of polytopes, they're getting assembled together, and at every stage of having group elements acting. When I take the trace, I'm kind of separating it out, and I'm taking just each piece of those polytopes, and like just each piece, I have just its own group elements acting, and nothing else is happening. So the idea is then, if I took the union of all those, there would be a comparison map back to my original sequence of polytopes. And the maps of the comparison would be covers, right? They'd be subdivisions. So that's enough to give a natural transformation from the composite to the identity, and therefore a homotopy on the realizations. Yeah, in this category, we don't formally invert the covers because we're taking the classifying space, so we don't really have to. I mean, you could, but if you do it right, you should get the same answer. Yeah, so that's why if you unassemble and reassemble, you get the same thing back. Because assembling pieces together is essentially, it's a path here, it's an equivalence. Okay, so scissors congruence K-theory is a homotopy orbit spectrum. So at pi naught, this recovers something that's been known for a long time, that the scissors congruence group is a zeroth homology of the group G with coefficients in K naught without any isometries. This is very easy to see. You can actually see this pretty much from the definition. There were like free abelian group, two relations. You impose one of the relations, and then the remaining one is P is equal to GP. So that gives you group homology. So this is also the homology of G with coefficients in what's called the Steinberg group of the geometry. So that's for Euclidean or hyperbolic. For the sphere, it's called something else. So, right, so it's known at the level of pi naught that this is a homotopy orbit construction. And not only is this known, but this is like really important. Like, those calculations of K naught that I mentioned earlier arise from this description. You take this Steinberg module and you start resolving it, and you get relationships between the higher homology groups of G with varying coefficients and this homology. And this is what allows you to get whatever K naught computations we've been able to get. So if you look at the work of DuPont, he has this great book that has like a lot of the details of how group homology computations are used to get scissors congruence groups. All right.
Wait, sorry, Cary, I got a little lost. Are we talking about K naught or higher?
Yeah, this is just K naught, and this was known.
So wait then.
group homology of G with these coefficients.
H0, right?
H0, yeah.
Covariance.
Covariance, exactly.
Okay, so,
Yeah.
the actual group homology will come up, right? Am I confused? Sorry. Yeah, I mean, of course.
It's a non-trivial module, so as you resolve this,
I'm confused because I thought when you say group homology, you mean the higher group homology groups and not just the covariance.
Mhm.
You mean
so the higher groups of G end up showing up when you're computing this H0. I mean, it's a long story. Yeah, okay. Okay, so this homotopy orbit result is now telling us something about the higher K groups, right? Not just K naught. So what is it telling us? Well, you know, this K theory spectrum is homotopy orbits of something. So what is that something? So now I'm just going to bombard you with some theorems. This something is a wedge sphere spectrum. So you can think of this as a Solomon-Tietz theorem for the spectrum. So I have a wedge sphere spectra, S zeros, homotopy orbits of that. That's Scissors congruence K theory. Even better, so that's a non-equivariant description. What it is equivariantly is it's a Tom spectrum.
Wait, there's now a G, there's no G on the left side, so I'm confused. KP of
Oh, sorry.
Okay.
There should be a G here.
Okay. Yeah.
I miswrote that.
And will this X show up on the wedge sphere?
It's a wedge sphere. So this is a free abelian group. So there's one sphere for every generator and a basis of this group. Unfortunately, you usually can't write down those bases explicitly, right? So this is kind of... But so you can do a bit better. This is actually a Tom spectrum. So what it is so you have this space, the Tietz complex of Xn. So this is a space that has one homology group, it's that group. You suspend it, and then there's a way of desuspending it by the tangent bundle of the geometry. So when you do that, it takes all those spheres and it bumps them down to degree 0. And then you get the homotopy orbits of that. And that description is equivariant. So that actually captures the action of the isometry group as well. So there's some great corollaries you get from this. So using this, we can make our first computations of higher K groups. So the higher K groups of polytopes in the line, it's kind of the simplest case to start. Let's just use translations. The ith group is the I plus first exterior power of the reals. If I take all isometries, I get the same for I even and 0 for I odd. So there's our first computations of higher K groups for scissors congruent spectra using this Farrell-Jones isomorphism. Another, maybe I'll state this as a theorem rather than a corollary because you need a bit more work to establish it.
And that coincides with the group homology of the group?
It turns out to be the group homology of the reals, but without the bottom homology and then shifted down by 1. So it has to do with the fact that this is a wedge. This space here is you take the reals with the discrete topology, and then you take its unreduced suspension. And then when you take homotopy orbits, this becomes a copy of the homology of R, and then this becomes something that kills the lowest homology class. Like it just becomes a single line and kills that. And then, so there's a bunch more work that I'm not going to describe, but in the Euclidean case, so for En, the higher K groups are, in every case, the higher homology groups with Steinberg coefficients. So using this Farrell-Jones isomorphism, we can get some computational results that start to give us access to the higher K groups. And what's especially exciting about it is that it's the same kind of description we had for K naught. So the same kinds of techniques that were classically being used to compute scissors congruence groups, we can now start to use them to get the higher K groups as well. Thank you.